So, welcome everyone along. Thanks for coming. Ron says that he's more than capable of introducing himself. So instead, I'll just let everyone know we're really grateful that he's come down here to speak with us, particularly with the ARC Training Centre for Innovative Hort Products. And with that, Ron, I'll let you get underway. Thanks.
Well, as the title says, I'm going to talk about the benefits of controlling ethylene around post-harvest fruit and vegetables. This is one of sort of many projects I've been fortunate to be involved with. Quite a long career in food science and technology, which really started in 1958 when, as a fresh-faced kid from school, I got a job at CSIRO as a lowly lab assistant. 1958 was also memorable. It was the first year I actually visited Tasmania. I came in a New South Wales under-19 representative rugby team, and we took on the might of senior rugby in Tasmania in 2 matches. The tour was quite a highlight on the field and off the field. I guess that's a story for another day. Over the years, I sort of managed to climb the greasy academic pole and ended up Professor of Food Technology at the University of Newcastle. I retired in 2005, mainly to get away from administration. They made me an Emeritus Professor and allowed me to carry on my research and pursue other hobbies. The one I put on the board is sort of pursuing at a slower rate each year. Right, we're talking about ethylene, the simplest of the unsaturated hydrocarbons. Although it's such a simple molecule, it's really quite an important molecule in evolutionary biology terms, because it's really one of the defining differences between plants and animals. Ethylene has no function at all in animals apart from being toxic at very high concentrations. Whereas with plants, it's active in all stages of plant development, from seed germination to senescence. And I've often pondered whether the ability to synthesise ethylene is actually one of the definitions you could make for a plant.
Ron, can I just make that big for you so we can see the whole screen? It'll look much better. Easier. How's that?
Now, the synthesis of ethylene is quite a complex metabolic part, but I've simplified it on this chart where you get methionine and there's this 2-step conversion to ethylene. Of course, they're all controlled enzymically. We've done a bit of a search, and with animal systems we can find quite a number which have AC synthase in some form or other. Some of it's corrupted, but we haven't been able to find an animal system which has anything resembling ACC oxidase. So one could postulate the definition of a plant as something which has an active ACC oxidase system. Anyway, enough of the philosophy. The actions of ethylene. Firstly, with climacteric fruit. I think everyone here is from horticulture background. Climacteric fruit, things like banana, tomato, kiwi, mango, peach, where they undergo a very defined ripening phase. And the action of ethylene is to actually initiate ripening, and then you get the marked changes in colour, texture and taste. With non-climacteric fruit, such as cherry, citrus, grape and pineapple, where you don't get these marked changes on ripening, and all vegetables, and what we're calling the vegetables are the non-seeded plant parts. These are all harvested at maturity, and ethylene here enhances degradation or senescence. Now, flowers can be climacteric, such as carnation, but most are non-climacteric, and they're similarly affected by ethylene. So while I'm talking mainly about fruit and vegetables, you can also apply it to flowers and other ornamentals. Right, so what's the source of ethylene that affect produce? It can come from the produce itself. It can come by synthesis of other produce in the chamber where it's stored. Ethylene being a gas has evolved and can be readily absorbed by other produce. It can come from exhaust gases from motor vehicles, notably forklift trucks driving around. It can come from leakage of natural gas pipes and cylinders, or it can come from industrial pollution of ambient air. Now what's important is that produce react to ethylene concentration. The source of the ethylene is irrelevant. So we're not talking just about ethylene synthesised by the produce, it's the ethylene the produce comes in contact with. And this was demonstrated to me in 1969, which I call my first important discovery for ethylene. Some of my other colleagues were doing enzyme studies on pea and wheat seedlings, and it was winter, so they wanted to grow their own, germinate their own seeds. So they built this plastic greenhouse. This actually wasn't the one, but it was similar to this, and they used fluorescent lights to simulate day and night. Seeds germinated okay, but when they came up they were all spindly and yellow. And they got me to have a look at it, and it looked just like ethylene damage. So we analysed the gas in there, and yes, it was a very high ethylene content. But where did it come from? We thought it might have been the breakdown of the polyethylene sheeting, but we found we couldn't find any ethylene germinate from there. So we pulled apart the fluorescent lighting, and we found it was in the ballast chokes. These are the voltage stabilising devices in the back of the fluorescent lighting, and the wires, the rings of copper wire which are lacquered, and they get very hot and the lacquer breaks down and gives off ethylene. So what they had to then do is rewire the fluorescent lighting so all the electronics were outside and just the tubes were on the inside. You can see we managed to publish a paper in Nature on this because it had enormous ramifications for the greenhouse industry, where people were using, in Northern Europe, were using fluorescent lighting during winter. Right, to the method hand. What's the post-harvest effect of ethylene concentration? Now, with climacteric fruit, as the concentration of ethylene increases, the time to initiate ripening decreases. So ripening starts faster. But once ripening is initiated, it carries on at a set rate. So it doesn't matter whether you've got a relatively low concentration that initiates ripening, they'll then all ripen in the same time as if you have a high concentration. It just occurs earlier. With non-climacteric produce, as the ethylene concentration increases, the rate of deterioration increases. So you get increased yellowing, loss of texture, rotting, off flavours, depending on the produce you're working with. So there's this distinction between how it works on climacteric and non-climacteric produce is important in what I'm going to say. So it then raises the question, is there a low concentration of ethylene where there is no effect? For many years, people used to consider the threshold level was 0.1 microlitres per litre or parts per million. In the work I'm going to talk about, I don't believe there is any level where ethylene is inactive, until perhaps you get down to 1 molecule per cell. So for all practical purposes, ethylene is always having an effect. When we looked at the research on low levels of ethylene, there is very little in the literature when we started to quantify the effect of ethylene on produce quality. There are quite a number of papers which cited 0 parts per million ethylene, but either they didn't measure it, or if they did, they didn't say what the limits of detection were. So we had no idea what naught is, and to me there's no such thing as zero. It's always less than whatever it is you can measure. And you'll see as I talk why I say this. So our experimental model was we held produce in an airstream at 20 litres an hour. We added ethylene into this airstream on a logarithmic scale of 1, 0.1, 0.01 and 0.001 part per million, which of course is 1 part per billion. The limit of detection we had with gas chromatography varied different days between 0.001 and 0.005 parts per million. So while I generally talk about 0.001, I'm really meaning less than 0.005. We then monitor the quality of produce over time and determine the time that produce becomes unacceptable, and that becomes our storage life. We looked at a range of climacteric fruit, and they all showed this typical pattern where there was a straight line relationship of increasing time to ripen as the ethylene was reduced on a logarithmic scale. Now we couldn't go down any further because we can't measure ethylene any lower. But it's fanciful to assume that this is actually the lowest level which is going to have any effect. With non-climacteric produce, and as I said, there's a range of conditions which denote senescence. For lettuce we followed the yellowing at 20 degrees, strawberry we followed rotting at 0 degrees, and with oranges we looked at chilling injury at 2.5 degrees, and they all show this sort of linear logarithmic increase in storage life as the ethylene concentration is reduced. Now, as I said, they used to consider 0.1 part per million was the threshold limit. So what I've done on this table is looked at the storage life extension that we got by reducing the ethylene from 0.1 to 0.001 part per million. I'm only talking about non-climacteric produce at the moment. And these are the produce that we stored at both ambient temperature, which for us is 20 degrees. In Hobart it's about 10 degrees, I guess. And then at the recommended low temperature. Now, the column says that's the day's extension, and I've just plotted here the percentage extension. Now, there's a bit of variation in the percentage increase, but when you look at the mean value, the overall benefit is quite substantial. There's about an 80% increase in storage life at ambient temperature and about a 60% increase at low temperature. So there's quite a big advantage to be gained by bringing the ethylene much lower than 0.1 part per million. The next question comes, well, what ethylene levels accumulate around produce during marketing? So we went to the Sydney wholesale markets. We went 4 times a year, which represented winter, spring, summer and autumn. And we measured the ethylene concentration inside boxes of produce on the market floor, and we measured the ethylene concentration in the air in the trading rooms. We took, as you can see, about 550 readings, so it was quite a big study. And with climacteric fruit, there's a very high range. The mean was 0.22, which to us is very high. It ranged from 0.03 to 4.92. And the very large range really reflects where there's apples present. Apples are such high emitters of ethylene, they really swamp everything else. Now, these levels of ethylene on climacteric fruit in the markets is not a problem because they're ready. It's a retail market, so they're ready to be sold. You want them to be ripe when you're going to sell them. But with non-climacteric produce, they're meant to be harvested ready to eat. You don't want them to be deteriorating. You see the mean ethylene concentration was 0.065, which is starting to get close to the 0.1 level. Again, there was quite a reasonable range, and this range would reflect the presence of climacteric fruit near these produce, so you're getting this cross-contamination. Now, even when we measure the ethylene in the air in the trading halls, it's quite high, and the mean is similar to the non-climacteric produce. Now, clean air normally contains 1 to 5 parts per billion ethylene. So the area in the trading halls is something like 50, 60 times higher than what it should be in clean air. And the contamination is due to the presence of climacteric fruit or motor vehicles, and you can imagine there's lots of motor vehicles driving around the trading halls. Near the Sydney markets there are 2 fruit distribution centres, so we went to these distribution centres. Again, we went 4 times a year. Measuring in Centre A, which was a mixed storage centre, there were 2 cold rooms, and you can see the ethylene level again is close to this 0.1 part per million. The ambient air is 0.03, which is well above what it should be for clean air. Now, with the fruit storage system, there was a room for kiwi fruit and avocado fruit. Now, these were not just transient rooms. These were rooms which held produce mainly from New Zealand, which was brought over and then stored and then released. So they were meant to keep them, stop them from ripening. But you can see from the ethylene it's really quite high, and they would have been ripening much earlier than they should have been. Even in the empty room, the ethylene is 0.3, which is quite high. You can see the ambient air in this distribution centre is more than double what it is in the mixed storage centre. We then went to supermarket stores. Now, in the supermarket stores, we're measuring the ethylene in the air. In the wholesale markets, we're measuring it inside the packets of produce. And we went to 7 retail outlets of the same supermarket chain, and we went back 7 times. So this is sort of the mean value we measured at the receivable dock, in storage and in the display units. And while you could say it was sort of lower than in the wholesale markets, for air in a supermarket it's still quite high. The last area we looked at was in domestic refrigerators, and we had 30 consumers, and what we did was we gave them a device which consisted of about half a metre of plastic tubing, which had a receivable container on the other end, and there was a hand-operated pump at the back end. So before they went to bed at night, they put the plastic tube into the crisper at the bottom, shut the door, and the first thing in the morning, before they opened the fridge, they used the puffer and collected a sample of gas and brought it to the lab. Now, we found the mean value of ethylene was 0.1 part per million. But the range was 0.01 to 0.59, but the difference reflected whether there were apples or no apples in the refrigerator. When there were apples present, the mean value was 0.2, and when there were no apples, it was 0.02. Okay, so what does all this mean? Firstly, it means that ethylene greater than 1 part per billion enhances senescence and ripening. So we've reduced the threshold level by 100-fold over what people thought was important. Secondly, in all market situations, ethylene is greater than 1 part per billion, and it's often greater than 0.1 part per million. So we must assume the storage life is suboptimal in all post-harvest situations. Therefore, any reduction in ethylene that we can make will be beneficial. The question then becomes, how do we create an industry awareness of the loss of market life that's occurring? And we thought, well, what we need to do is create some ethylene standards. So what we did with all the data we generated for produce we stored, the value that we obtained at 0.001 parts per million, we said was 100% of the potential market life. And we translated all the other values that we got at higher ethylene as a percentage of that. So we could then plot this regression equation of potential market life against ethylene concentration, and we got this regression equation. Now, so we're saying 100% potential market life, I said was at 0.001, but on the graph we said, look, let's not say it's 0.001, we call it 0.005 just to push it up a bit. So then you could go down and say, well, when we've had if we lose 10% of potential post-harvest life, we can go along and we can see the ethylene concentration that we get, and you can pick any other point along here. We've chosen 70%. You can go along and say that's the ethylene concentration that produces 30% loss of post-harvest life. And we use these to propose standards for non-climacteric produce we're only talking about at the moment. So for retention of top quality, you need to keep the ethylene less than 0.015 parts per million. And if you do this, you get less than 10% of the potential post-harvest shelf life being lost. Now we're saying an unacceptable rate of quality loss is if you store the produce greater than 0.1 parts per million ethylene. Because of this concentration, you're getting 30% potential post-harvest life lost. Now if we go back and use these standards and apply it to the wholesale markets, the distribution centres that we talked about before, and so they're the number of values here, and I've pulled out those which we considered were low, so they were less than 0.05, and those which were high, which were those greater than 0.1. Now you can see in the wholesale markets there was only 10% of produce which were in the low range. None of the rooms in the distribution centre were in this range. And the air in the supermarket stores, there was only 1/3 of the spaces which qualified. In domestic refrigerators it was 17%. Again, it broke up to those who had apples and didn't, and most people have apples in a refrigerator. There was a big bulk in the medium, but there was generally more in the high class than there were in the low class. So there's considerable scope for work to be done to meet the standards if one accepts these as a reasonable standard. Now I've said I was talking about non-climacteric produce because climacteric fruit are quite a different proposition. And this is the data we got for the loss of time to ripen at 20 degrees. Now, this data is not relevant during marketing, as I said, because you want ripe fruit to be marketed. It's applicable when you're wanting to store or wanting to transport. And you can't produce an overall standard because you can see from here there's an enormous range in sensitivity of fruits to ripening. Bananas, you've only got to sort of put a sniff of ethylene somewhere near it and they go off. And kiwi fruit are not far behind. Whereas things like peach, avocado and tomato, you could almost bash them over the head with an ethylene cylinder and they'd sort of just shake their head and something. Oh, and I put the mean value at the end, but it's rather meaningless. For climacteric fruits, you're going to have to look at the sensitivity of the particular commodity and work out what ethylene range you can tolerate. Right, so what are the opportunities arising from this research? Right, with produce itself, we can say for non-climacteric produce, any ethylene is harmful, so any reduction you can make, there's a benefit to be gained. Now, this also applies to ornamentals because most of them are non-climacteric, and there should be much more interest in this area because flowers particularly are really high value commodities, and one of the treatments they're using is silver thiosulfate, which blocks ethylene action, but there's a lot of problems with disposal of the solution because of the silver waste. People just pour it down the drain. The third area is in organic produce. That reducing ethylene obviously is an acceptable treatment for organic produce because you're not applying anything synthetic. The second area we need to go into is to start measuring ethylene levels. If we promote the notion of quantitative standards, you need to go out and start measuring ethylene in real situations. One of the big problems here, there is no cheap, quick method to be able to measure ethylene. Most of them involve taking samples, sending them to a lab, and you get the results in a few days. You know, I draw the parallel with temperature, where anyone who stores food, they know the temperature of their room because they set it on a dial, there's a thermometer hanging there, and they walk in, they can see, they know what the temperature is. We've really got to get to the stage where there's some device there which hangs, or you just click it and it tells you what the ethylene is, and then you know whether you've got to do something or not. Third area is with consumers, and I'm only talking here with domestic refrigerators. Most households have apples and they're big ethylene emitters. You can buy devices to put in the refrigerator which are supposed to absorb ethylene, but to me you need some visual indication to say either these devices have expired or you've got a problem and you should do something. At least move the apples out anyway. Okay, so that was the end of really the first phase of what we did. Then we come on to what I call the new research paradigm. Current technology in the horticulture industry is all focused on cool chain management. The rate of ripening and the rate of senescence is directly related to temperature. So reduction in temperature inhibits post-harvest deterioration. Refrigeration is now the technology of first resort. If you go to any post-harvest technology and say they've got a problem, they tell you to reduce the temperature. The ideal is to hold produce at low temperature on the farm during transport in markets, in the retail and in the home. And in many situations this cool chain, a consistent cool chain, has been effectively maintained. Now, there have been considerable benefits from this. There's a much more extended trade reach, like you can send your Tassie lettuce up to Darwin, as Matt was saying earlier. You get a longer season. I mean, you can buy, I'm sure, down here, American stone fruit now, Mexican mangoes, and they buy our stuff out of season, and we're getting much better quality. But the world at large has changed, and this reflects around the concerns for a sustainable environment. Refrigeration was introduced in an era of low energy cost. Now, reducing greenhouse gas emissions is an international priority, and the actions in many countries has the effect of increasing the cost of energy. There was a paper published by Andrew East in 2010 where he looked at energy usage in a range of situations, and I've just pulled some of the data from his paper where refrigeration of horticultural produce in California uses 1 billion kilowatts of energy. That's a lot of energy. The marketing of fruit and vegetables in the UK accounts for 3% of the total CO2 emissions in the UK. Now, the horticulture industry is coming under pressure to reduce energy usage. Firstly, it's in their own interest to reduce costs, but also they want to be seen to be socially responsible. So it raises the question, is a cool chain always necessary? And if you ask this question, you're branded a heretic. Cool chain management is what we do, and people can't perceive or have difficulty perceiving that you could do it any other way. My answer to the question is not always. Why? Firstly, you need to meet the market need only. I'll come back to this in a minute. Second is, can you use an alternative lower energy technology? Right, on meeting market need, the recommended storage temperatures that we use commercially have been developed by researchers who store the produce, and they say you get the maximum market life at this temperature. But most produce is marketed well before the end of the possible market life. So why have you got to go to this very low temperature when you're not storing it that long? On the alternate lower energy technology, producing ethylene gives a similar effect to reducing temperature. It inhibits ripening, it inhibits senescence, and inhibits rotting. So our research question became, well, what is the interaction between temperature and ethylene with storage time? And our first model was bananas. Bananas is the most internationally traded horticultural item. I think more than half the bananas produced in the world are sent on international trade. They're harvested when they're mature but unripe. They're invariably all transported to market refrigerated at 13 to 15 degrees. This is the lowest temperature they can use because you get chilling injury at lower temperatures. The lower temperature inhibits ripening by reducing ethylene production, and it reduces the sensitivity to ethylene. So you need a higher concentration to initiate ripening, and it takes longer to produce this amount of ethylene. The bananas are then ripened at the markets with ethylene. Well, we've looked at it domestically and internationally. I'm only going to talk today about the domestic situation. 80% of Australian bananas are grown in North Queensland. And the major markets, of course, are in Sydney and Melbourne, and the distance they have to travel is about 3,000 kilometres. They are all sent by a refrigerated truck. The first cost to note is a refrigerated truck costs you 25% more than a non-refrigerated vehicle. So if you could do away with refrigeration, the growers would immediately save 25% of their costs. Right, we then looked at the relationship between ethylene, temperature and time to ripen. And we used our same 4 ethylene concentrations. We looked at it at 15, 20 and 25 degrees. And we found, as you'd expect, as the temperature decreased and the ethylene decreased, the time to ripen increased, and it followed this sort of pattern. Now it fitted a regression equation, which was the log of the green life and the log of the ethylene concentration and the temperature. Now from that equation I've pulled off this data which looks at the 4 ethylene concentrations and the 3 temperatures we used. And you can see the time to ripen ranges from 3.5 days at 25 degrees and 1 part per million to 35 days at 15 degrees and 0.001 parts per million. But I want you to focus on 0.1 part per million, where it goes from 8 days up to 15 days. And we're going to look at, is it able to transport bananas without refrigeration? Now the first line is the data that I had previously. 15 days at 15 degrees, 11 days at 20 and 8 days at 25. Now the travel time from North Queensland to Sydney is 1 day 23 hours, and to Melbourne is 2 days 6 hours, which says about 2 days. You say, oh, you're very precise. How do you know it goes 1 day, 23 hours? Well, we do know quite accurately because the route they're allowed to take are mandated by the highways industries. They're told, depending what type of truck they go, which roads they must take. The time they drive is mandated. The out time of rest they must take in between is mandated. So they all stop at the same place all the way along for the same amount of time. So they all arrive within an hour of what's been set out. So the travel time is 2 days. If we allow an extra 3 days for delays before and after transport, we've got 5 days. But hey, this 5 days, it's lower than 8 degrees at 25. It's certainly a long way below 15 days at 15 degrees. We're now transporting at 13 degrees, so you'd be even higher than that 15 degrees. Now, because the truck route is mandated, we know where they stop and how long they stop, we could go to weather records and we modelled the temperature over the 4 seasons. And I'll just summarise it here. In midsummer, January, I put this because I give the talk in the Northern Hemisphere, you've got to tell them that some are different in other parts of the world. The average temperature was 25 degrees. So to meet this 5-day transit time, you can cope with 0.6 parts per million ethylene. In winter, the average temperature was 14 degrees, and you actually cope with 0.9 parts per million, which for bananas is really quite high. So without refrigeration, you can get bananas to Sydney and Melbourne. Now, you may need to think about having some way of reducing ethylene in midsummer, because obviously you get some patches where it goes up higher than 25. So for insurance, you could add some ethylene absorbent package into each box or into the container. The other issues which possibly need to be considered are, rather than the load being too hot, we found there's more of a problem with the load being too cold in winter, because the refrigerated trucks in winter is actually insulating the cold from the outside. When they come through the granite belt in Queensland, it's quite cold, in New England and New South Wales. And the other is you've got to be able to manage the water loss depending on the technology you use in transit. Now, what I'm proposing is not radical, it's old technology. This is a picture of a louvered rail van. It was designed in CSIRO in the 1930s, and it was designed to move bananas. The design says that all these vents on the side here, as the train moves, air moves through the vents. They designed it to stop the temperature going up, but in fact it also kept the ethylene down low. And these trains were used to move bananas all around Australia up to about the 1950s. They then moved to trucks, not because the rail vans didn't work, but because you had double loading. You had to put it on a truck, take it to the railhead, then reload it onto the rail van. At the other end there wasn't a problem because the rail vans went right into the Sydney markets, and I think they went into the Melbourne markets as well. But the railways in those days were not very responsive. So you loaded the van up and it may leave today, it may leave tomorrow. So they then moved to road, but it was because of the poor organisation of the rail network. So what we're really turning is back to the future, but doing it with trucks rather than rail. Right, I want to come on to what is our most recent research, and it's mainly with non-climacteric produce. And it focuses on, can higher temperatures meet market need? Now I put the font in red as a caution, and it really applies, I guess, to all the data, even the ones I've spoken about before. Our data on post-harvest life relates to laboratory handling conditions and the standards we accept for acceptable quality. they can be different to commercial parameters. Like we don't drop our boxes of fruit and vegetables on the floor and throw them around, so they don't get rough handling. The temperature is also more consistent. I think look at the relativities between the temperatures and ethylene. That's really what I want you to focus on. Well, the first study we did was with broccoli, and deterioration in broccoli is yellowing and rotting, and the recommended storage temperature is 0 degrees. So we did a usual study like I did with bananas, where we stored them in 0, 5, 20, 10 and 20 at the 4 ethylene concentrations, and this is the storage life. So it ranges from 2.5 days at 20 degrees with 1 part per million to 64 days at 0 degrees with 0.001 parts per million. But hey, who wants to store broccoli for 64 days? Even if you got 1 part per million, who wants to store it for 40 days? So what we did was we calculated the regression equation for this data like we did with bananas. And then we stipulated the market life we wanted and looked at the combinations of temperature and ethylene that we could get. And this is the data in the bottom. So storage life for 7 days at these ethylene concentrations, that's the temperature you need to store it at. So at any market life you want, if you went from 1 part per million to 0.001 part per million, you could increase the storage temperature by 4 degrees. Now, if you wanted a storage life of 14 days, which to me would seem reasonable for most broccoli transported within a country, even if you had 1 part per million, you only need to store it at 5 degrees. If you had good ethylene control, you can store it up to 10 degrees. And, you know, if you're talking about Tasmanian winter, hey, that's ambient. You don't need any refrigeration. We did the same with green beans. Here the deterioration is yellowing and rotting, but the recommended storage temperature is 5 degrees because they're sensitive to chilling injury. And this is the sort of result we got. As you'd expect, the highest storage life is at the lowest ethylene concentration, the lowest temperature. We then calculated the temperature you need at different ethylene concentrations for different storage life. And the first thing you should notice is that it's much more sensitive to ethylene than broccoli. If we look at 14 days storage life, if you've got 1 part per million, you could store them at 5 degrees. If you can control it to 0.001, you can store them at 18 degrees. So even in Sydney, you're talking about ambient temperature at 18 degrees. Now you might think, well, are these relevant to market levels? So we went to the market and we measured the level inside Hessian bags of green, and it came up at 0.22. Now this is sort of a log scale, so 0.22 is actually halfway between 0.1 and 1 part per million. In styrofoam boxes it was even higher. The mean was 0.55 and it ranged from roughly 0.3 to over 1 part per million. So the values up here in this range reflect what's happening commercially. So if you can get down here, you've got great scope to increase the temperature. Extending this further, we said, well, what about unrefrigerated marketing in tropical regions? In many developed countries, refrigeration is either not accessible or is too expensive to use. Produce is exposed to temperatures of 30 degrees plus, so as you'd expect, there's rapid deterioration. So the question was, can ethylene removal give you sufficient extension in market life? Now I've gone straight to the table. Here a cucumber was stored at 10, 20 and 30 at our usual ethylene concentrations. Now as you'd expect, the storage life increases, the temperature goes down and the ethylene concentration goes down. But you can see at 10 degrees in 0.1 part per million, you get the same storage life as at 30 degrees in 0.001. If you look down the 30 degree column, if you had 1 part per million ethylene, you've only got 3 days storage life, but at the lowest you can get 16. Now 16 days is quite a long storage life. We also looked at pak choi, and it was interesting. I sent a paper in with pak choi, and the referee's comment, I think he was from Midwest America, "What's pak choi?" You should put a picture in. Here we only looked at 30 and 20 degrees, and as you'd expect, the great extension at 30 degrees, the lowest ethylene concentration was similar to 20 degrees at high ethylene concentration. Within the 30 degrees, you've got about a 1.5 days extension over 1 part per million. You could say, well, what's 1.5 days? 1 day means a lot. We're talking a lot about growers who put them on a truck and they may move them 400, 500 kilometres to market. Roads are not very good, there's often delays, and often they can reach the market at the end of their market life. You give them an extra day and you've got a chance to sell a higher proportion of their crop. Again, we tried to simulate the relevance of this to a commercial situation. Produce, and we looked at sort of Cambodia and Laos. Produce is often sold in unsealed plastic bags, and at 30 degrees the ethylene accumulates to about 1 part per million in these bags. So these conditions here really represent commercial reality, and if you can get it up to there, you've got a marketing advantage. We also looked at bitter melon, and this was quite interesting. I mean, as you can see, they're all a bit different. There's very little difference between the market life at 20 and 30 degrees, particularly at low ethylene. At 30 degrees, where they diverge is that high ethylene concentration goes off much quicker. So if you can reduce the ethylene concentration from 1 part per million down to less than 0.1, you've got an extra 2 days storage life. Now, people can say, oh, well, 1 day, 2 days, what does it matter? But this is a picture of bitter melon after 3 days at 0.001 and 1 part per million. They go off very quickly, so 1 day, obviously the one on the right is not marketable, whereas the one on the left is quite marketable. The last example I want to give is degreening of lime fruit. As you know, the price for lime is very high for green fruit. When it gets to the stage of looking like that, it's lost about 80-90% of its value. So there's a lot of work being done to try and retain the green skin colour. And the recommendation is to store at 5 degrees, which is just above the threshold for chilling injury. Now you should note that things like oranges, you don't want them green, so they degreen them commercially by storing them at 25 to 30 degrees in ethylene at 1 to 5 parts per million. So the industry associates degreening with high temperature and retaining green colour at low temperature, which was why they then worked on developing the technology for limes. But you can see we stored limes at 5, 20 and 30 degrees, and we were most surprised to find the lime stored at 30 retain green colour much longer than those at 20 and longer than those at 5 degrees. Not only that, but those at 30 degrees became relatively insensitive to ethylene from 0.1 down. So that in tropical, subtropical countries, you could store limes at 30 degrees. Now, we haven't looked at 25, so it may not be the optimal temperature. You're saving energy. A lot of these places don't have refrigeration, and it's even much better than 5 degrees where you've got 0.1 parts per million ethylene. All right, so what comes next? I suppose in many ways we feel we've exhausted the laboratory studies. I mean, yes, we can go on and look at other things, but we roughly know what the story is. What we want to know is, can this information be applied to specific commercial situations? So what we need to do is to identify a post-harvest chain where quality maintenance is an issue. In other words, industry says, yeah, well, we could do with a bit more of life, or their costs could be high where you may want to reduce it. What we want to do then is measure ethylene levels at all stages within the chain. And from this determine at which stages ethylene accumulates to a high level and could benefit by being reduced. Maybe it's through the whole chain, but it may only be in a number of steps. Apply an intervention technology to reduce the ethylene, and then, and these are the really important ones, to measure the effect of the applied technology, like how far did it reduce ethylene, and then measure the quality improvement at retail level over the untreated. In other words, what was the actual benefit you got in the marketplace? And there are virtually no studies in the literature which look at the whole chain and determine the ethylene levels, how you can reduce it, and then measure the quality at the end of the market. Most studies do like we did with the Sydney market. You go there and you measure ethylene here and there, but you don't know where the stuff came from, and you don't know where it goes to and what the end effect was. All right, so what are the technologies you can use to reduce ethylene? First is you can oxidise it to CO2 and water mainly. Now there are lots of oxidising materials. My preference is for potassium permanganate because you can use it in air or modified atmospheres. It's relatively low cost, it's flexible, you can put it in small or large packages, it's mobile, it's relatively safe. Lastly, it's acceptable to the organic industry. They say you can use permanganate in sachets as long as it doesn't come into direct contact with the produce. You can have physical removal, like just ventilate with ambient air. Air is free and there's an endless supply. You know, particularly on sea shipment, where sea air should be very low in ethylene. All you need is a fan and a heat exchanger. Then you can use a combination of oxidation and physical removal. And there's a product out of the UK called It's Fresh, which is really a zeolite clay with a palladium catalyst incorporated. Now I won't go into the technical details, but essentially it has a dual effect at absorbing ethylene onto the clay, and some of the ethylene is oxidised on the palladium catalyst. The question's in my mind, does it have sufficient capacity to, say, run a container load? It seems okay for small units like strawberry punnets. The fourth area is inactivation. And again, I've mentioned before how silver thiosulfate is used in the flower industry. Obviously it's not used in the fruit and vegetable industry. But 1-methylcyclopropene, or 1-MCP, is starting to become used, certainly used in the apple industry. Its mode of action is that it has a similar structure, physical structure, to ethylene. Now ethylene works by binding to the enzyme which triggers ripening, and MCP preferentially binds onto these sites, and it binds very tightly, so ethylene can't get onto the active site and initiate ripening. So while it's very good at inhibiting ripening, there's a problem with a lot of fruit when you want to ripen them. how do you get the MCP off there so you can ripen it to market? And they found a lot of them, you get uneven ripening during marketing. Now, strangely enough, the MCP is a patented technology. I've done a lot of work with MCP on non-climacteric produce, and it works very well, but they've shown very little interest in using it. The advantage of non-climacteric produce is you don't have to turn on a later stage, so you can have it permanently. It doesn't make any difference. Part of the problem with MCP at the moment is it's a fumigation technique, so there's logistical issues in having to fumigate a batch for 4 hours, 5 hours. They're moving to a solid delivery in a package, but we'll see how they go from there. So there's a range of technologies which could be used. The final slide. This is a slide taken from our research in 1989, which is 17 years ago. 27 years ago. This is the control sample, and I want to consign that to history. I still find, when I buy a punnet of strawberries, I invariably throw out the last few because I don't eat them fast enough. We made up sachets of potassium permanganate, and this is what they look like. The industry still doesn't use it, and it's such a simple technology. The only place in the world where I know that it's been introduced is actually in Kuala Lumpur, where Carrefours now insist that all the strawberries they buy from suppliers has to have a sachet of potassium permanganate in. And It's Fresh is trying to work with Sainsbury's in the UK to try and get their product. So I think there is considerable scope to use low ethylene as an alternative to refrigeration. It's not going to be an easy task, or it can be used as an adjunct to refrigeration to extend the marketing range of what you're doing. Okay, thank you.
Thanks very much for the talk, Ron. Maybe first we'll have some questions, and then maybe we can head up to the tea room and have some more sort of personal chats with Ron. But any sort of general queries about the talk that you want to ask me?
In Asia, there is on the farm to the consumer, there is a wide variation in exchanges and temperatures. How, by the use of, say, an ethylene absorber or something like that through that system, they'd have to be changed several times.
Well, I'm working on that. They're currently sending it through a system where it goes like that. If you can reduce the ethylene and still send it through the same system, you're getting a benefit throughout some parts more than others.
Yes.
So the benefit to the transporter in the end, he doesn't have to do anything different except do some intervention at the beginning, and he gets a benefit. Yes. It's ideally, in our society, we say, oh, you take all this out. You know what I'm saying? This is the minimal technology. So we had a professor, Susie Newman, with this Cambodia. Now, they started using MCP, and I wish they'd come and spoken to me earlier, because I would have got them onto something simpler, where they're trying to bring it from the growing areas down to Siem Reap, where the tourist areas are. There's a lot of scope in many of the developed countries to supply the tourist resorts, but you've got to have the high quality and the pretty crappy roads in a lot of these places to get it there, so you need the extra time to preserve the quality.
Any more questions? I'm obviously curious that there's a lot of fruits that produce very high levels of ethylene. Why is apple such a serious issue?
You'll have to ask her up there. But apples is not only odd in that it produces so much ethylene, it's actually harvested post-climacteric, but doesn't go soft until it's well post-climacteric. And this is why they've worked it well with MCP, because you're not depending on the apple to go soft. So they can get it in and stop it, the ethylene action. And the biggest problem they tended to face was the flavour wasn't always there. But again, there was trial out of Germany on this energy savings aspect, and someone looked at these apple stores holding them at 3 degrees higher than what they're doing now, and they actually found the quality of the apple was better out of the 3 degrees, because one of the problems at low temperature in controlled atmosphere with ethylene control is they tend not to develop the same apple aroma, but at the higher degrees they're good. They did. So they not only saved energy, and you calculate the energy was enormous, the amount of energy they saved, because they're storing them for 9 months. But they actually got an apple which was rated better by the consumers.
Final question, we'll thank one for his time.